I think we've got a few examples today happening now, especially in social media, and I'll come to them. And if you're reading the description of this particular episode, you will see that this has happened recently. And what I'm talking about is, it's not I can't say that it's exactly pseudoscience, as just a scientific error. And a scientific error that, if only it was presented early on in Popperian terms, in a critical way, a critical rationalist way, then the embarrassment, the shame, the damage to people's reputations, the over-enthusiasm, we want curiosity, but the over-enthusiasm can sometimes lead to waste of money, waste of time, waste of energy, a distraction from otherwise good research that's going on. The most famous example of this that is known throughout the physical sciences, at least, is what is known as the cold fusion debacle. And I became fascinated by this when I was at university, because, of course, the things that I talk about here on Topcast are the things that I've been interested in for 20 years. And so the process of science, the methodology of science, the philosophy of science, epistemology, and all of that, it all comes to bear on when science goes wrong, or, looked at through another lens, when science goes right and corrects things. So if you're not aware of it, the cold fusion debacle happened in 1989, a historic event in the history of science. And I almost wanted to use the word perpetrated by, but that's not the right word. It was research conducted by Martin Fleischmann and Stanley Pons, who've been, immortalized, essentially, as being emblematic of when science goes wrong. But as I say, looked at another way, it can be seen as science going right. Now, these two guys, they're chemists. They came from chemistry, they're working at the University of Utah, and they announced to the world via press conference that they'd achieved nuclear fusion at room temperature. And that's what cold fusion is. Cold fusion is the fusion of, it could be protons, groups of protons, nuclei, helium nuclei, whatever it happens to be, but nuclei of atoms together, such as the sun does. The sun accomplishes it at 15 million Kelvin. Now, let's just go to the physics as to why it happens at that temperature. So far as we know, it tends to require that temperature because positive charges repel each other, and the closer they get, the more strongly they repel each other. And so if you want to fuse two protons together, that's the simplest case, which are two hydrogen nuclei, then you have to overcome what is known as the electrostatic force of repulsion between them. And the closer you push them together, the more they repel. Until you can think of, mind you, it's not a perfect analogy, but think of each proton as being covered in a kind of superglue, so that if you can get them close enough, they will stick. And then energy is released. And that's fusion. Now, how do you get them close enough? Well, one way to get them close enough is to have them moving fast enough so that when they crash into each other, they have such momentum that it overcomes the electrostatic force of repulsion. They're traveling so quickly, so fast, that they hit each other and stick. And then fusion happens, energy is released, the sun shines. That's how astrophysicists explain fusion. That's how nuclear physicists explain fusion. And therefore, it seems to rule out the possibility of having this thing called cold fusion. After all, how else are you going to overcome the electrostatic force of repulsion? Well, there are numerous approaches, and here I'm going to big up Sabine Hossenfelder. If you go to Sabine Hossenfelder's YouTube channel, she has, well, I've only seen one. I think she has more than one video on cold fusion, but there's one there where she goes through all the different ways in which cold fusion just might work. And it's a wonderfully produced video, because at the end of each time she says, here's a way that it could work, and then she says, there's just one problem. She tells you why the damn thing won't work, why this particular methodology just won't work, or is very difficult to implement in practice. One method is muon mediated cold fusion. The muon is kind of like an electron, except it's heavier, and if you can replace the electron around, let's say, a nucleus of hydrogen, a proton, So hydrogen contains one proton and it contains one electron. Replace the electron with a muon, or better yet, you might use tritium or deuterium. So heavy hydrogen that contains one proton, one neutron, and then an electron. And if you replace the electron with a muon, then what happens is the muon can shield, essentially, the two protons that you're bringing together, the two nuclei you're bringing together, such that maybe they can fuse. Now, the just one problem, amongst many others, is muons are short-lived, so they don't last very long. So they will decay into other products, but also they're difficult to produce in the first place in large number without consuming a lot of energy. So the amount of energy in to such a system that produces muons to use muon-mediated fusion tends to be more than what you get out of the fusion reaction. In theory, maybe that's a route to having actual cold fusion that works. Look that up. So when Pons and Fleischmann in 1989 said to the world, hey, look, we've demonstrated cold fusion in our chemistry lab they were using deuterium oxide. They were using heavy water. So deuterium is heavy hydrogen, heavy water is D2O. So instead of having H2O where you've got hydrogen, you replace the hydrogen with heavy hydrogen. So they were using heavy water and they were using a palladium electrode. And they detected more heat coming out, supposedly, of the reaction vessel than what was being pumped in. Now, this is the usual setup for something like electrolysis. Okay, electrolysis, you send electricity into your electrode and you do something in a solution of water. So this was just water and just a palladium electrode. And they said they were getting more heat out of the reaction vessel than what was being pumped in via electricity. Well, astonishing if true. The problem is, from a Popperian perspective, they said not, here we have an unexplained amount of heat coming out of our reaction vessel. We don't know why. They should have published a paper, but they went to the media. Should have published a paper basically saying that. They could have, of course, said in the paper, we think just perhaps it could be cold fusion. But that's one explanation among many. Experimental error could be another. We haven't properly measured the amount of energy going in and the amount of energy coming out. We want people to check using our experimental apparatus what's going on here. Maybe it's cold fusion. We're not saying it is. But they didn't do that. They didn't tell the world all the ways in which they could be wrong, at least initially. They said, we have demonstrated cold fusion. I don't know how certain they were, although I was watching about 3 months ago, the interviews they did soon after. They went on a big media tour and there was front page headlines and all that kind of stuff. They got a lot of press and media. They got a lot of money initially. But science works on a method of error correction, and part of error correction is having other scientists try to replicate your results. Some people said they did, but the majority said they didn't. And in particular, of course, the nuclear physicists, because they were not nuclear physicists, they were electrochemists. Nuclear physicists were saying, yeah, this is impossible. Here's the theoretical reasons why it's impossible. We've tried to replicate it. We can't replicate it. And ultimately, of course, it was revealed it was just an error. They hadn't achieved what they did. But the meta error was them saying that they knew the explanation when they didn't know the explanation. Cold fusion is one explanation among many for why you might be measuring more heat coming out of your reaction vessel than you're putting in. The chief reason that you should automatically jump to is you've made a mistake, because it would seem that you're violating conservation of energy. So that would be the first thing you would want to say. But if you're not violating conservation of energy, then yes, you're generating energy within that reaction vessel in some way. Now, how this could be muon mediated, I don't know. It can't be, but there's no muons being created there. So there wasn't a good explanation of what was going on, and simply saying cold fusion wasn't enough. They did say some other stuff, but I don't think it was persuasive to anyone who was an expert in the area, which is, that can ring alarm bells. It's not disqualifying, but you should take notice. And so this is, often cited as a cautionary tale in science about how to do science or how not to do science. Don't say you know the explanation if you're an experimentalist, if you don't know the explanation. And by no, we mean good explanation. Checked, submitted to peers who are critics of yours. Okay, I'm not saying it has to be published in a peer-reviewed scientific journal or anything like that, but it at some point has to encounter other people to count as science, to count as a good explanation. Otherwise, you'll never know. Well, Pons and Fleischmann found out. So there's a sense in which this is also an example of science itself working, absolutely working, of correcting the error, but of the scientists themselves making an error. Now, the reputations of these two did suffer. Pons and Fleischmann, they're now renowned. They're well known. They're known most for that. Now, who wants to go down in history as being known for? Well, in the worst case, many people think of them as frauds, absolute frauds. They were pushing an idea they knew to be false, and they doubled down on it. And in fact, I think, well, they did. I can't remember which of them just went off and continued to do more work on. It was, I think, Korea. I think Korea sponsored them. A university in Korea, or research institute in Korea, gave them money. Or was it Japan? I can't remember. Actually employed them for quite some time to try and replicate the results. Of course, they never could. He never could replicate the results. And so, again, a demonstration of science ultimately working, of a bad explanation or a bad set of results being corrected by the entire apparatus, which is the culture of science in the form of other scientists checking and criticizing what these results or ideas were. So you need to have reproducibility for things to be science. You need to have peer review, and you need to be critical. All of these ingredients are there as kind of moral imperatives, the shoulds that you need to have before you can figure out what is the case in science. The morality of science, what should be the case, is prior to what goes on in the lab.